The fluid application being studied is the flow over an airfoil and the effects of increasing angles of attack. The story of the airfoil is as old as the Wright brothers. The main purpose of the airfoil is to create lift, which is mostly due to the angle of attack and shape of the airfoil. When orientated at a suitable angle, the airfoil deflects the oncoming air to produce a higher velocity streamline on the top of the airfoil and a lower velocity streamline on the bottom of the airfoil. This difference in speed is paired with a pressure difference that creates a higher pressure on the bottom side of the wing. The resultant? Lift. The coefficient of lift of an airfoil works rather intuitively. The amount of lift the airfoil creates increases as the angle of attack increases until a certain point where the flow behind the airfoil begins to separate and the lift decreases. This point is called the critical angle of attack. Once the flow behind the airfoil separates, the separated flow dominates the characteristics of the flow, such that increasing the angle of attack more actually produces more drag and less lift. This critical angle of attack is dependent on the airfoil profile, but is usually in the range of 8 to 20 degrees. But studying airplanes is rather boring. A much more interesting application is the use of airfoils to generate downforce. Since the 1960s, the world of performance auto racing has utilized wings to improve the aerodynamic efficiency of the cars to create downforce. Previously, cars have been limited to the amount of mechanical grip they can create in order to go faster. The implementation of wings and aerodynamic grip has increased the car's ability to maneuver tighter corners at faster speeds. There are many theories on the appropriate angle of attack for the automotive applications. But with higher temperatures and lower speeds than their high-flying counterparts, does the automotive wing have the same critical angle of attack? Can wind tunnel testing provide the information needed? Although the wind tunnel testing is interesting to look at, it doesn't provide the whole story about the flow characteristics over the wing. Thus, the flow needs to be modeled in ANSYS Fluent to give more detail on the physics that is at play. The governing equations for describing the flow over an airfoil are Bernoulli's equation and Moody equation. Additional derived equations include the equation for the lift coefficient, drag coefficient, and the Mach number. In order to compute the fluid flow around the airfoil, a mesh was utilized that had a very high aspect ratio around the boundary layer, but a much smaller aspect ratio at areas away from the airfoil. The high aspect ratio was needed in order to accurately compute the compressible flow. The physics of the domain were modeled as steady and density-based. The main differences between the flow of the airfoil in a racing application versus an airplane is the temperature, pressure, and velocity differences. For each attack angle, the Mach number was only 0.1314, which represents the typical speeds of a sprint car at 90 miles per hour. The pressure used was standard pressure at 101 kPa, and the temperature was 90 degrees or 305 Kelvin to represent the temperature of the best day of the year, race day. Just like in that last video, stability and consistency and accuracy is important in running analysis to ensure the program or code does not crash. The method used to solve this flow was an implicit method. This is more stable than the explicit method and leads to faster conversions of the compressible flow. The flow, turbulent kinetic energy, and specific dissipation rate of the fluid was all solved for using a second-order upwind discretization. Although these selections are more computationally expensive, they are required in order to converge a more accurate solution for the compressible airflow and accurately predict the drag. Overall, this solution is second-order accurate. As far as consistency is concerned, there is no previous solution to the system being solved. Empirical tests can be conducted on the airfoil to determine consistency, but results do match the physics as expected. The base case study for an airfoil was on a 1.55 degree attack angle. As can be seen on the static pressure contour graph, there is a stagnation point on the leading edge of the airfoil and lower pressure above the airfoil than below it as expected. The Mach number contour also shows the expected results with a higher Mach number or velocity above the airfoil than below it. The 5 degree attack angle still shows a significant difference of pressure between the top and bottom of the airfoil. There is also a starting of some turbulence air on the left side of the airfoil, as can be seen by the blue on the Mach number contour. The 10 degree attack angle also has significant static pressure difference, but the turbulence behind the airfoil has increased. The 15 degree angle of attack was a final simulation run. In the Mach number contour, you can clearly see a significant amount of turbulence on the top side of the airfoil. This turbulence significantly affects the lift on the airfoil, as will be shown next. Based on the 4 simulations run, it can be determined that the critical angle of attack is somewhere between 10 and 15 degrees. This can be determined by the change in lift coefficient from 1.0 to 0.74, and also by the drag increasing significantly between the 10 and 15 degree angles of attack. To further narrow down the critical angle of attack, more simulations can be run between 0 and 15 degrees. In this case, the stock airfoil was analyzed and using the pressures and temperatures and velocities of a sprint car application. To further refine the analysis of the angle of attack, the next steps would be to model the exact dimensions and geometry of the sprint car wing and import them into Fluent. Until the engineering analysis is done on these parts, racers around the country will continue to throw detailed engineering out the window and replace it with a feel of the seat of their pants. This feel they have for the car will guide them to determine the appropriate angle of attack to produce the most downforce with the least drag and hopefully propel themselves into the winner's circle.